kick things off. So reminder, homework 1 is due essentially tomorrow night. I know it says Saturday, but it's at 6 a.m. So make sure you get it in by Saturday at 6 a.m. Today we are finishing up the DML stuff. So we will be talking very quickly about insert, delete, and update. And they're very easy commands, so we won't spend much time on them. Then we'll talk about subqueries. And finally, we will get into the data definition language for SQL today. So remember, direct manipulation language means how you manipulate existing data in the database, so how you can query it, how you can update and modify it, whereas the DDL, data definition language, refers to actually declaring a new database, declaring relations in that database, declaring the fields within each relation, and the data types, the primary keys, the foreign keys, so on and so forth. So we'll go through that pretty quickly because it's pretty easy syntax, and for the most part, you can just as easily look at my PowerPoint slides as listen to me talk about it. Okay. So, oops, we don't want to look at that. We want to look at the end of chapter 6. So, we're getting to, let's say, modification statements. So that is insert, update, and delete. What we covered the previous 2 days were queries that simply returned existing information from the database. So we want to look at how we add additional information, how we delete information, and how we update information. If you want to insert a new row or new tuple into a table, the keyword is insert into, and the name of the table, then the keyword values, and essentially a comma-separated list of values that you're inserting. So I'll actually go straight to the example because that's the easiest to see. So here I'm inserting a new tuple into staff, and I'm giving it these values, and they need to match. The order in which you present the values need to match the order in which the columns occur in the relation, because it's simply going to match the values with the columns. And if you don't want to provide a value for a field, what is the value you provide? Null. Very good. And that's only legitimate if that column has been declared as optional, meaning it doesn't require a piece of data. You're also allowed to specifically identify the columns for which you are providing values. So here we are specifically providing values for these columns. In this case, you don't have to follow the order of the columns in the relation. You can give them in any order you wish, but of course, when you then give the values down here, the domain type of that value must match the type of the column. And that's helpful when you don't want to provide values for all the columns, specifically for optional columns. So in this case, there's a couple optional columns that you are not providing values for here. There's 2 nulls. So back, and I forget what those columns are, but in any event, by specifying the column names for which you are providing values, you are able to avoid having to use nulls. That's usually the only reason you provide column names. I have never used this form in any program. I always just say insert into a relation, values, and then I provide values for each field. Okay. So insert's very simple. It's unconditional. Okay. By contrast, if you want to update an existing tuple, so you simply want to modify an existing tuple. Maybe someone got a raise, maybe they changed their address, maybe they moved to a different branch. So you're updating an existing tuple. The keyword is update, and you give the table name, then a series of one set keyword and a series of assignment statements where you're assigning to attributes. And then here you almost certainly need a where clause because you want to only update certain tuples in the database. So for example, here everyone is getting a 3% raise. So this is unconditional. Every tuple in the database or in the staff relation will receive a salary increase of 3%. Whereas in this case, we're restricting the salary increases to managers only, so it's where position equals manager. Okay, so just one set statement. I don't know if I have an example. Here we go. So here I'm modifying two attributes, and you'll notice there's only one set statement, and the two assignment statements are separated by a comma. Okay. So questions about update. It's also pretty simple. Okay, finally delete. This is where you're deleting tuples from a relation. Be really careful with this one because if you forget the where clause, you are toast. And I've done it before. And you do not want to be in the building when I do that because a good portion of the building hears about it. Okay. Turns out that occasionally I have a temper, and that has happened when I have deleted an entire relation because I was at the command line and I forgot the where clause. Okay, you forget the where clause, it doesn't delete the relation, but it deletes every tuple in the relation. So the where clause, pretty darn important. So in this case, we are deleting from the viewing relation the property whose value is property number is PG4. Okay, so and there at the bottom, you can see how to delete all records from a table. Probably don't ever want to execute that. Okay, the reason you don't ever want to execute the bottom one, if you really are looking to get rid of all the records in a relation, it's probably because you want to delete the table. There's a DDL command to delete the table. Okay, this doesn't delete the table. It leaves the table there. It just removes every single tuple in the table. Okay, and just like you have insert into, you have delete from. You just got to remember those keywords. Any questions? Short, simple. Yes, Thomas. Yes, that's with the DDL. Okay, so what you're talking about is structure of the relation as opposed to modifying values. Okay, so in a moment when we get to the DDL, the command is called alter table, drop, and then the column name, and that would drop the column. Okay, but that's a DDL. Other questions? Okay, so move from there into subqueries, which you have already briefly seen. Okay, so a subquery is just a query that contains nested select statements. So here, this one right here, this select statement you see down here is a nested select statement. It is a subquery. So the way they're evaluated is inside out, meaning the most deeply nested one is evaluated first. So this one would be evaluated and it returns a single scalar, which is the branch number for this particular branch. And so now you'd be comparing the branch number with, say, maybe B003. Okay, so that's a very simple scale subquery, and it is called a scalar subquery because it returns a single value. And you saw that previously with aggregation operations. Remember, previous lecture, we wanted to find the minimum GPA, and we also wanted to find the student associated with that minimum GPA. And the issue is that you can't do that because the student's name could not appear in the select list because it can't appear with an aggregation operator. In this case, what we are doing is we want to find all staff whose salary is greater than the average salary at their branch, and we actually, not at their branch, actually period, so across the entire firm. So we want to find all staff whose salary is greater than the average for all staff, and we want to know the difference. So for example, if the average salary is $17,000 and I'm a staff member making $25,000, then it's going to print out $8,000 for me. If I'm a staff member making $10,000, since I am less than $17,000, I will not be in the output. So only staff members making more than the average salary. And you can see there's two nested queries here. So the first one is selecting the average salary from staff, and the second one is exactly the same, selecting the average salary from staff. In both cases, they return the same value, but in this case, so if it's 17,000, here's what it resolves to. Salary minus 17,000, where salary is greater than 17,000. And this may look inefficient, but a good query optimizer should probably realize that these two queries are the same and only perform them once. But does anyone remember an alternative way we can save the value? Variable. And how do you prefix the variable? With an @ sign. So we can save it into a intermediate or temporary variable, select average salary. Remember, colon equals, not equals, colon equals. Does anyone remember where colon equals comes from? Does anyone ever seen the language? That's not, okay, maybe. That's not the one I had thought of, but bash predates the language I'm thinking of, so you might be right, Thomas. You've never seen Pascal. Pascal used to have this irritating convention that assignment statements required colon equals. But bash predates Pascal, so maybe they took it from, well, or they may have taken it from, but Pascal may have taken it from bash. So I was looking for the originating language, and you might have it. Okay. Yep. At any rate, you need the colon equals, and then you can just put it in both places in the query. So minus at average salary, where salary is greater than at average salary. And when you do the select statement right here, where you assign to average salary, it actually produces an output at the command line. If you don't want that, if you want to suppress the output, then you probably don't care. But if you want it to suppress it, you would say select average into. So it's a little different. No assignment statement, more stuff to remember. Ugh. So that was a scalar one. And one thing I want to point out is that almost every query not involving aggregation can be expressed as a join, every subquery. So basically, it appears to me that many subqueries were there because end users don't know how to do joins. And so they put subqueries in as an alternative to joins. Now, if you're doing an aggregation operation like min or average, you need a subquery. But for example, if I just want to find the staff who work in the branch at 163 Main Street, I can do that with a join statement. Okay? So I can just say select the staff right here from staff branch, where the staff's branch number equals the branch number, and the street is equal to 163 Main Street. I don't need a subquery. So to me, most of these subqueries, you use them because you don't know how to write a join. But you need to know about them because they exist. So three types. Scalar, we just talked about. Then there is something called a row subquery, and it essentially returns a table, and you use them with the exists predicate. So here, we are trying to find all staff who work in a London branch office. So we select a staff number and their information from staff. And what we're doing here with the subquery, here's the subquery right here. We're selecting star from branch B, where the branch number is equal to the, the staff's branch number is equal to the branch's branch number, and this branch's city is London. So you'll see scoping comes into play here. So this S, see this S right here, refers to this outer S. So it's looking outside that subquery. So what essentially happens is for each staff person in the staff tuple, it will perform this query. So it will substitute in that staff member's branch number. It will use that as an index into the branch relation. And if they find that staff member's branch, then they'll check to see if that branch's city is London. Okay, and if it is, it will return, in this case, a single tuple, because it is the only tuple returned is the branch at which this staff member works. So either the staff member works at a London branch or they don't. Okay, this is incredibly inefficient. Okay, because for each staff member, it is performing this query. There's a much simpler join that does, oh shoot, I don't have it. So let's write the join solution. In fact, I have it, so I'm going to try to make the notes bigger. Nope, come on, not there. Make this bigger. Okay, let's see if we can't. Okay, so there's the equivalent join solution right there, where you're simply doing a natural join. Wait a minute. No, this isn't the same one. Sorry. There we go. This is the right one. So we select the staff information from staff natural join branch where city equals London. I also think this is a much more readable query, right? So we're just doing a natural join of the staff with the branch where the city is equal to London. And we're just selecting staff where the city is equal to London. I think that's a lot more easy to read. But some people, they find it easier to write it the other way. And if that happens to be you, that's fine. Although in a test, you need to know how to write the join version. I will tell you on a test, I will not require you to write a row subquery because I just find them super complicated. Yes?
So in the other example, you join instead of exists. Say like on the right table, it matches.
Just like, let me bring it up,
Yeah,
okay? So that we can all see it. That's not what I want. Slide sorter. Sorry, something's taking time. Wow. Come on. Can we be any slower? Okay, there we go. So what's the question now?
So when you join, sometimes it will basically return every match found on the right-hand side. So you have duplicate columns, rows. How would you, so it exists though, from my understanding, it would only return one, right? So is there a way with that join to prevent duplicate?
It's up to the query optimizer. So the query optimizer is supposed to be, so first of all, it is not, so each staff member presumably has only one entry for them, right? So they work at only one branch.
Right.
So this join is only going to return one tuple for each staff member.
Right. There's just, let's just say this was a different table though, where there's a possibility on the branch table, so this was some other table, and there could be multiple entries for that staff. It would return
all of them.
See what I'm saying?
Yep.
So is there a way with a join to prevent?
You say select distinct.
distinct.
Yep, and then that will cause the solution to eliminate all duplicate tuples.
Okay, cool.
Okay, so you can't necessarily eliminate the duplicates. No, you can't eliminate them other than by saying select distinct. Okay, the distinct keyword will say get rid of the duplicates. Okay, the previous query is no better. If there were duplicates, it would do exactly the same thing. This query and the previous one are identical in terms of results. Okay. Now, I will say there is a time when I can see this type of query being done. And that is, remember last time we talked about set difference, where you want to find all, let's actually take a look, refresh your memories. So last time we had, say, professors and administrators, which I'll abbreviate ADM. So we want all administrators who are not professors. And the way you write that is with a set difference. So you want all administrators who are not professors. Okay, well, that operation is supported in normal SQL like Oracle SQL. It's not supported in MySQL. And in fact, the way that you would have to probably write this query in MySQL is as follows. You would have to say select, say, name from ADM where not exists. Select name from professors. I'm going to name this A, this P, where P.name equals A.name. Okay, so here's, I don't know how to get a set difference without using a row query. So this is an example where you do have to use a row subquery. So it's saying select name from administrator where it does not exist in the professor's relation. And that's the only way I've ever seen to write set difference in MySQL. So that's an example of a row subquery, and I don't know any way to get around it. Keep that one in mind because that is useful for doing set difference. Questions about that? Okay. Moving on. So we've had scalar subquery, we've had this row subquery. So the scalar subquery returns a single value, row subquery returns a table, and then we have a table subquery which returns a table, except it uses in rather than exists. And it returns a row subquery can return as many columns as it wants. A table subquery can only return a single column. And apparently the only difference is whether you're using exists or in as your keyword. So if it's exists, it's a row subquery. If it's in, it's a table query. Got it? Memorize it. I don't see much sense in it. So a row subquery is a table with multiple columns. A table subquery is a table that can only have one column. Table subquery uses in. Row subquery is used with exists. Okay, so here's one where we're listing all the properties that are handled by staff who work in the branch at 163 Main Street. And you can see we actually have two nested subqueries. So this one down here, the innermost one, what type of subquery is that? This one right here. What type of subquery? You got three choices. You got scalar, row, table. Nope, not row. Why do you think it's row, though? I'll ask. Was it just a guess?
No, so what's the other one?
This one, right here. Select branch number from branch where street equals 163 Main Street.
It doesn't have any.
Pardon?
It doesn't have any.
Doesn't have what?
Any.
Correct. So it's not a table subquery. So you got that right. It's not a table subquery, so now we're down to row or scalar. But it returns just a single value, right? There's only one branch that's going to have the street equals 163 Main Street. So in fact, it is a scalar subquery. Okay. This one is the second one right here. This one is the table query because it's using in. So now we are selecting all staff who are in the branch at 163 Main Street. Okay, so essentially we are collecting here. So let me see if I can't use the pen. Give it a go. Okay, so, oh, there we go. So this query right here, come on. Nope. There we go. This query right here is returning all staff at 163 Main Street. And the query optimizer will probably do this query once and then cache the result. So for every property, what it's going to do is remember that the property for rent has a staff member who's managing it. So it's taking the staff number from each property and checking to see if that staff number is in this set. And if it's in that set, then it's going to return that particular tuple. Okay? Makes sense? And you can write that as a join. So take a couple minutes and do it. So what I want is to list the properties that are handled by staff who work in the branch at 163 Main Street. So take a couple minutes. You can work on it with a neighbor. See if you can't write that as a join. And you have all the all the attributes you need are shown there. You don't need to know about any of the other attributes in any of the relations. Yes.
PropertyForRent have a staff number?
It's pardon?
PropertyForRent, does it have staff number?
Yes. So the reason you know that actually is it says where staff number. This staff number actually is referring to, so that's scope stuff, scope information. Okay. You may not have finished it yet, but I'm still going to go over the solution. I'm on the wrong slide. Okay. So you can do it with a series of natural joins. So I'm going to move up here. And basically, you just do a series of natural joins. So you just join the property for rent with the staff. So that gives you, remember, the property for rent has a staff number. For each tuple in property for rent, you have a staff. So you're going to use the staff number in property for rent to look up that staff member in the staff relation. That's that natural join. Then you use the staff. Now once you're into staff, so let's just see if I can't, not sure if I'm going to be allowed to use any kind of ink. Nope. Okay. So let's do it. Try this. Okay, so you have, let's use black. Okay. So you have property for rent. I'm just going to say property. And it has some property info. And then it has a staff number. And then you have the staff relation, and it has a staff number, and importantly, it has a branch number. And finally, you have a branch relation, and it has a branch number, and it has the street. So what you're doing is for each tuple, you're going through the property relation, and for each tuple, the tuple has a staff number. So that staff number is being used to find the corresponding tuple in the staff relation. Okay? Once you have that tuple in the staff relation, you can find the branch number at which that staff member works. So now you natural join that with the branch relation. So you're basically looking up that branch number now and using it to find the corresponding tuple in the branch relation, and now you look at its street to see if it's equal to 163 Main Street. So it's a three-way join. So you end up with joining PropertyForRent with staff, and then joining that with branch, and then saying where the street is 163 Main Street. And that's a lot more succinct than writing this verbose puppy. Okay, but do you all see how that join was done? So, yes?
So if you wanted to do a natural join, like say for some reason you wanted to join branch and staff on PropertyForRent, is there any way to do that?
No, because there's no, wait, so you want to join them on property number?
I'm not for this instance.
But for something else?
Yeah, for something else you want.
No, because they don't, so neither the staff relation nor the branch relation has a property number in it. You can only perform a join on attributes that exist in the relation. So neither branch nor staff had an attribute called property number. So you can't perform a join between them on property number.
What I was asking is if you have this table and you have these two tables, if you want to natural join both of these tables off of this one.
No.
Okay. That's all right.
You have to kind of link it the way I did. So you're able to link PropertyForRent with staff because they shared a common attribute, and then you could join staff and branch because they had a common attribute. So you have to find a way, in effect, to link them together through a trail of common attributes. Other questions? Okay, so turns out, remember I said you could use the exist to do set difference, but you can also use a table subquery to do set difference. So let's say again that I want to find all administrators who are not professors. Okay, so I had the original one. This was with not exists, but I can do the same thing. I can just say select name from ADMA where name not in select name from professors P. Right? Because this subquery right here gives me all the professors, and this returns, this right here returns true if the name is not in that set. So you can also use not in. Let's just take a show of hands. How many think the first query is easier to read or easier to write? Just for you, naturally. How many think the second query is easier to write? Okay, I agree. I find the second query a lot easier to write and read. So I still don't really see the reason for a row query, but that's just me. Okay, so any questions about subqueries? Okay. So basically, I only care if you can read them. I don't care if you can write them. It's, as far as I'm concerned, for the most part, okay, I'll take that back. If you can perform it using a join, I generally think it's better to write the query using a join. There's a couple times where subqueries seem to be indispensable. One is for set difference. I don't know how to write set difference using a join. I've never seen it. So you can use a table query as an easy way to do set difference. You could also use a row query. The second time where I don't really see an alternative is where you have to use the scalar subquery as an intermediate result because it is the result of an aggregation operation. So here where I want it, the all staff who made more than the average salary, I don't see how to write it any way other than a subquery. Okay, I can assign the result to an intermediate variable like average salary, but the fact remains I'm using a subquery. So those two cases, one, you need to use the aggregation result from a subquery. Two, you need to do set difference. I think you have to use subqueries in those two cases. Any other case, I think you can use joins. Okay, so make sure you know how to read them. On a test, I'm not going to make you write one. Is that clear? But on a test, I could write one for set difference and ask you what operation in the relational algebra, which we haven't gotten to yet, but we will. I might say, which operation does this one implement? And I expect you to say, if I give you this query right here, I expect you to say it implements set difference, because that is important, since MySQL does not support set difference. Okay. Another time to take a deep breath. We're changing topics again. Okay, so far today we've considered two different topics. So first we started with updates, deletes, inserts, and that was data manipulation. Then we talked about subqueries. So this is the third topic. This is data definition. So we're changing now. Before, we were just talking about values in a database. Now we're talking about the structure of the database. How do we define new relations? How do we define which fields those relations have and what their types are? How do we remove relations from the database? Or as Thomas at one point said, what if I want to remove a column from a relation? Those are all done with the data definition language. Okay, so also with the data definition language, you can specify integrity constraints on data. Remember null? The null one was optional, so you can specify if a column is optional, meaning the value is optional, such as a viewing column for a property for rent. If a client goes to see the property, they may optionally leave a comment. So that is the null integrity constraint. Remember, there is entity integrity, which means that the primary keys must be unique and non-null. So the data definition language gives us a way to specify a primary key. It gives us a way to specify referential integrity. What was referential integrity? Remember something about foreign keys? Very good. Well, unless a primary key. So when you insert a tuple that has a foreign key, you can only insert it if that foreign key points to a valid primary key, or the foreign key is null, one or the other. So that's referential integrity. You can specify that with the data definition language. And the fourth type of constraint was general business type constraints, such as no staff member can manage more than 100 properties, or no staff member can make more than $100,000. Data definition languages allow you to specify those constraints. And finally, data definition language allows you to define and maintain views. So we've talked about views. You'll see how you can specify them using SQL's DDL. Okay, there's a whole bunch of data types in SQL. I'll let you read them because they're not so different in general from the ones you're already familiar with, so let me just quickly hit on the ones that are not the same. So first of all, you're allowed to have either fixed-sized character fields or variable-sized character fields. So char 4 is a fixed width field. Varchar is a variable width field. The difference, if In a fixed width field, if your string is not, in this case, 4 characters long, it will be padded with spaces. In a varchar field, you'll get a field that is exactly big enough to accommodate the string. Okay, so it's pretty clear why you use varchars. They save storage. Fixed width fields can waste memory. Yet it's actually more common to use fixed width fields than varchar fields, even though varchar fields waste memory. Why? Right, so that's a waste of space. So that's a total black eye for fixed width fields, and yet they're more commonly used than varchar fields. So they must have some advantage that overrides the fact that they waste space. So they're not more flexible. They're because they actually can't shrink, or varchars are in some sense more flexible because they can expand or shrink. Pardon? Right, so you're getting at it. So it has to do with the placement of data. If it's fixed, then you know the size of the record. Every record is the same width, okay? Which makes it a lot easier to index into it, like arrays, right? Arrays require that you know that every element in the array have fixed width, or else indexing into it doesn't work. So the advantage of fixed width fields is they lead to fixed width records, which makes it real easy to index into them. So fixed width fields are faster to access. It's faster to access records with fixed width fields. With variable length fields, it becomes more of linear search because you never know how big they are. So that's the trade-off, speed versus space. Okay, there's tricks you can play with varchars, like putting them off in a separate relation, but it's tricks. Okay, so you see a lot of fixed width fields because they're faster. Okay, this is from business. Comfortable to me because my first language was COBOL. This is going to seem weird to you. So in business, they really don't like the fact that certain values like 33 cents cannot be exactly represented with a floating point number or a double. Okay? Why do you think businesses aren't really enamored with the fact that 0.33 is actually represented as like 0.329856 by the computer? What if you have 1,000,000 transactions? What if you're a thief? There's a slight difference between 0.33 and 0.32985, right? It doesn't matter much for a single transaction. What about 1,000,000,000 transactions? You could get rich off that difference. People have gotten rich off that difference. Okay? There were, in the early days of computers, some smart programmers who figured out there was profit to be gained from the fact that you could not precisely represent certain numeric values. And they took advantage of the fact that businesses transact hundreds of thousands or millions of transactions to skim the difference. So banks and businesses find it really important to precisely represent even cents. Okay? So in a database, there is a difference between 0.32985 and 0.33. So because databases are frequently used in businesses, there is a data type called numeric or decimal. They are the same. Why they use two different names for the same type, I do not know. But at any rate, they store those things as strings and not as numbers because it allows them to precisely represent the number. Okay, so you'll often see things like salary or the price of an item represented as decimal 7,2 because you can precisely represent that value, the cents value, as a string. And then they can convert it into a number if need be. So that says that the number is actually 7 digits, 2 of which are the decimal point. This isn't C++. In C++, what would the 7 represent? Would it be the total number of digits? If I said printf 7.2f, what would the 7 represent? Code of character width. And what would that include? The decimal point. You would only get 4 digits in front of the decimal point. Not so here. That is the total. 7 is the total number of digits. You get 5 in front of the decimal point and 2 after the decimal point. That's different than printf. Just tuck that away. Okay? 7 is the total number. So 7 minus 2 is 5. That's how many digits you get. If you don't care about being precise, you can use float or double just like you would in C, C++, or Java. But there's a difference between float, double, and decimal. And you should know that difference because businesses care a lot about that difference. Okay? You use numeric or decimal, you're storing those things as strings, and you get precise storage of the decimal digits. You specify it as float or double, it will be stored as a 32 or 64-bit number, and you will not be precise. Okay. We have dates. We already talked about dates, time, and timestamps. I won't bore you by talking about them again, but they are built in SQL. Intervals, the same way, because you have intervals between days. So one date minus a second date gives you a number of days. Okay, that's not a date, it's days. Subtracting 2 time will give you maybe minutes or hours or something. So intervals are another actual data type, and you're allowed to specify it as with the keyword interval. So this is saying you give the top end of the interval first. This is a year down to the smallest part of the interval. So you're saying that this interval is up to 99 years and 11 months. This interval is as high as 99 hours and 59 minutes, 59.999 seconds, because here the seconds refers to the number of decimals in the second. Okay, we good with the data types? They're pretty simple, but if you're not, feel free to ask a question. Okay, so moving on to the integrity constraints. So I just talked about them. There's optional columns. So if you don't say not null, the default is it can be null. Okay, so if you want something to be required, you say not null. So here we're declaring a column named position. It's a varchar of length 10, not null. It's required. Okay, in SQL you can have domain constraints to control what are the legal values. So there's a check keyword that checks to see, and then you can give a SQL query inside of check. So here we're asking, is sex in the set M or F? So we're limiting the characters to M or F. Okay, let's see if I get here's another one. We're checking to see if the value is in select branch number from branch. So we're selecting all the branch numbers from branch and saying that it can be any value that's in branch number currently. And in SQL, you can create new domains. In C and C++, you do it with typedef, right? You have typedef to create new types. In SQL, it's create domain. So create domain is like typedef. And you give the new name, and then you give the data type. So that's different. In C++, you give the data type first and the domain name second. So it's just reversed. And then you're allowed to give a default value for the domain. And then you can limit the values that are allowed. So here, create domain sex type as char, check value in. Okay. Here, create domain branch number, and you're allowing as char 4, but you're further limiting it to be just the branch numbers in the branch relation. Okay, so that's creating domains. With entity integrity, that is in SQL implemented by allowing you to specify a primary key. Keyword is primary key, comma separated list of attributes in parentheses. Only one primary key per relation. So I'm just giving an example of two different primary keys. You're also allowed to say that you have other keys by saying unique, in which case you are saying that this is a attribute or set of attributes that could be used as a key. What do we call those keys if they're not a primary key? They're a candidate key, and once they've been rejected as the primary key, they're still a candidate key, but they were rejected, so now we call them, not secondary, good guess, alternate keys. Okay, so an alternate key is a candidate key that did not become a primary key. Say primary key wannabe. So you can say unique is a way of specifying alternate keys. Okay, it's a requirement that those combination of attributes also be unique. Okay, and any field declared unique has to be declared as not null. Makes sense because two nulls would be not unique. Okay, third one, the way SQL allows us to implement referential integrity is by declaring, using the foreign key keyword, you're allowed to specify that an attribute or combination of attributes is a foreign key, and you can indicate which relation they are indexing into. So in this case, you're saying that this foreign key is indexing into the branch relation, which means we can do a natural join with the branch relation. Okay? It also means that SQL will check when you insert a tuple that that branch number exists in the branch relation. So you should not have to say that yourself. SQL should be enforcing the fact that when you insert this tuple, that the branch number you're providing is a valid one in the branch relation. That's why you have to say references, so SQL knows which relation to go checking to make sure that the foreign key exists. Now, foreign keys present a problem, just like pointers present a problem. So what happens when in C or C++ when what you're pointing at is deleted? What's it called now? Dangling pointer. Well, you can get that problem in a database too. Let's say that we have a staff member who works at branch B003 and we try to delete branch B003 from the branch relation. That would create a dangling pointer, right? So what we have to do is specify what action to take if we attempt to update or delete. See these keywords here, update or delete? What happens if we attempt to update or delete a primary key? That could have dangling pointer implications for the foreign key. So SQL gives us 4 options that we can, or 4 actions that can be taken when we try to delete a tuple from the parent relation. First of all, we can cascade the change, meaning we will find all foreign keys that depend on this tuple and delete them as well. So we'll delete the tuple from the branch relation, and we will cascade that change by deleting all staff at that branch from the staff relation. Which might mean if we keep cascading, that we delete what from the property relation. If we delete all staff who were working at branch 3, and now we keep cascading, what might happen in the property relation? What might we have to delete? Properties managed by that staff. So you have to be careful with that cascade option because it could end up deleting a whole lot of tuples. It may cascade not just from the parent to the child, it could keep cascading from the child down to a grandchild and keep cascading. So you have to be careful. Okay, the second option is to set null. Remember, it's okay to set foreign keys to null. So that's what we often do, right? With a pointer, we just set it to null. So that's an option. It's called the set null option. Or we could make the foreign key revert to a default value. So that foreign key, when you specified that column, you may have specified a default value. Maybe when staff are removed from a branch, they're assigned to the headquarters branch. That's the default branch. Okay, so that's an option. And fourth, you take no action. You say, hey, just like we may not want to delete something until all pointers to it have been removed, we may take no action. That's the Java solution, right? Java won't delete something, won't garbage collect something until there's no pointers to it anymore. So the Java solution is the no action solution. It won't delete it from the parent unless there's no pointers to that parent. And that's the default. If you don't, in SQL, specify one of the other 3 options, you get the no action option. And as it turns out, that we just covered delete, but it's the same thing for update. You have to specify one of those 4 options for update too. Makes sense, right? You're changing to a different branch number. It's just slightly different for cascade. What do you think happens with cascade on update? If I change B3 to B7, what do you think cascade does? It changes it. So it changes all B3s to B7s. So it's just a slightly different thing. Otherwise, but set null and set default and no action, those are the same. Okay, so there are some examples. This is SQL syntax now. So foreign key, staff number, references staff, on delete, set null. What's happening on update? No action. I didn't specify anything. The default is no action. So if I don't say anything, and I didn't say anything for on update, there's no action. So for delete, we're setting it to null. For update, there's no action. It won't allow it. Okay? Questions about referential integrity? Okay? General constraints. So those are business constraints. So we're going to use the check command for them. And inside the check command, you can put any SQL query that resolves as a predicate. So there you're using in or exists, which means in effect you are doing a row subquery or a table subquery, but they're really not subqueries because there's only one select statement. Okay, but that's essentially what you're doing. Is exists is associated with a row subquery, in is associated with a table query. So here, what we're doing is we're saying that no staff member can manage more than 100 properties. So we're just checking, and the check says not exists. So any staff member, if we insert a tuple and it causes that staff member to be over the limit of 100, the change would be rejected. The tuple would not be inserted because it would violate this check constraint. You're allowed to name these checks by saying constraint, staff not handling too much, and that will allow us to drop the constraint if we want. If you don't name the check, there's no way that you can later delete it because there's no way that you can access something that's unnamed. So if you want to give yourself the ability to delete a check, you need to name it. The way you name it is with the constraint keyword. Okay, and there it is. Constraints can be dropped using the alter table statement. Okay, this is great. You can do all kinds of integrity checking in SQL. MySQL is public domain, and doing all that constraint checking requires lots of free coding, which has not yet been done. So you can't do a lot of this stuff in MySQL. Create domain is not supported in MySQL. The check is not supported, and foreign key references are not supported. They're parsed because they hope that someone will be kind enough to donate their time and implement them. So you can check your syntax, but you can't, it won't actually be enforced. However, MySQL does give you the consolation prize. It does have the enum type. Ooh, gives you a lot of power there. You get to enumerate all of the allowable values. That's not quite as powerful, but at any rate, it works occasionally. Here is a type for gender, which is M or F. Okay, so in the homework assignment, homework 2, you're supposed to do DDL, and you will be asked to do a full-on SQL implementation of integrity constraints. Guess what? You won't be able to check it using MySQL. You just got to try to do it based on my slides in the textbook. Sorry, but that's the way it is. I once had someone say, well, why would you make us do the assignment if it's not supported in MySQL? Because eventually you go out into the real world where people have bucks and they can afford Oracle SQL, and then you can use this stuff. Okay, so I want you to know the SQL way you do in SQL. Okay. Thomas asked how we can do certain things after we've already created a table. You do it with the alter table command. And if you want to delete a table, you do it with the drop table command. Okay, you can create views and drop views. We'll talk about that on Tuesday. We won't get to them today. We will not get to indices at all until we get to physical design. Okay, I am not going to go through, I went through the individual parts of the create table command. So here is one that kind of shows you it with all the elements brought together. So create table, name of the table, in parentheses is all the stuff for the table. In C, C++, that would be curly braces. In SQL, it's parentheses. In C and C++, the type goes first. In SQL, the name of the column goes first. Then you get the type, and then things like not null or unique, and you get default values. They're comma separated, unlike C++, which uses semicolons between the fields. SQL uses commas. Here's a constraint, a named constraint down here. Then after you have all of your column declarations, then you do your other constraints where you do your entity constraint for primary key, all of your referential integrity stuff. You're also allowed to put additional constraints down here as well. You don't have to put them with the attribute. You could put them down here in the after section as well. Okay, and finally, for today, what can you alter after the fact? After the fact, you can add or delete a column. You can change the type. I'm sorry, you can't. You can change the type of a column by deleting it and then adding it back. That's how you change the type of a column. You can add or delete table constraints, and you can either set a default for a column or remove a default for a column. And there's the syntax. It's very easy. I'll let you read it. And drop table, very simple. Drop the table, and you can, if that is going to remove some dependent objects, you can cascade or restrict. Restrict says don't do the deletion if it would leave dangling pointers. Cascade says kill them all. Okay, it means cascade to basically delete all dependents as well as this table. Okay, so any table that had a foreign key that referenced this table would also go away. That's what cascade does. Okay, so that takes care of the basic stuff for the DDL. Tuesday, we will talk about views and how you create them, and we'll get into the theoretical underpinnings of relational databases by talking about the relational algebra. So have fun finishing the homework, and I'll see you on Tuesday.